Hello, so my name is Tiffany Natasha, and I'm gonna explain about the Fermat's little theorem for Math 22 discrete math. So basically, Fermat's little theorem states that if P is a prime number and if A is an integer number, then A to the P is equivalent to A mod P. In particular, if P doesn't divide A, then A to the P minus 1 is equivalent to 1 mod P. So here's the history behind the Fermat's little theorem. So Pierre de Fermat first wrote what would become his little theorem in 1679. As was typical of Fermat, he did not include a proof for fear the proof would be too long. The first proof of this theorem was published more than 50 years later by Leonhard Euler in 1736, using the modular arithmetic notation published by Johann Carl Friedrich Gauss in 1801. Euler's proof can be presented in a shorter and simpler fashion. Euler's proof using modular arithmetic notation is presented as the classical proof of Fermat's little theorem. So the most modern concept necessary for the proof of Fermat's little theorem is either Taylor's theorem, which was published by Brooke Taylor in 1717, or the binomial theorem, which was published by Blaise Pascal in 1665. Both of these theorems lead to the same result. It shows that mathematicians had the necessary mathematical machinery to prove Fermat's little theorem well before Euler published his proof in 1736. So, what is the Fermat's little theorem? It's actually if P is a prime number and A is a natural number, then A to the P is equivalent to A mod P. Furthermore, if it doesn't divide, then there exists some smallest exponent such that A to the D minus 1 is equivalent to 0 mod P and divides. Hence, so A to the P minus 1 is equivalent to 0 mod P. This theorem is basically called as Fermat's theorem. So as I said before, let P be a prime number and A be any integer number, then A to the P minus A is always divisible by P. In modular arithmetic notation, this can be written as A to the P is equivalent to A mod P. For example, 11 is a prime number, so 2 to the 11 minus 2, if we put it on the calculator, it gives us 2046 as the result, which is divisible by 11 by Fermat's little theorem. There are some ways to prove Fermat's little theorem, but here I prove it by using the induction. So the first step is using the best case, which is 0 to the P is equivalent to 1 mod P, which is obviously true. And then suppose that the statement A to the P is equivalent to A mod P is true, then by the binomial theorem here, A plus 1 to the P equals to A to the P plus P1 A to the P minus 1 plus P2 A to the P minus 2, and so on until P minus 1 A plus 1. Note that P divides into any binomial coefficient of the form Pk for k is between 1 to the P minus 1. This follows by the definition of the binomial coefficient as Pk equals to P factorial divided by K factorial times P minus K factorial. Since P is prime number, then P divides the numerator but not the denominator. Taken mod P, all of the middle terms disappear, and we end up with a plus 1 to the p is equivalent to a p plus 1 mod p. Since we know that a to the p is equivalent to a mod p, then a plus 1 to the p is equivalent to a plus 1 mod p. So by using the proof of induction, we can prove that Fermat's little theorem is true. So I think that's all.